So there are many ways of learning mathematics, and one of my favorite ways is really a three-step process. In the first step, you start with a motivating problem. Now, this problem may not be from mathematics itself. In fact, it's better if it's not. It's a problem from another domain, maybe computer science, data science, physics, social sciences, something like that. So you start with a motivating problem, and then you come to a mathematical concept to solve that problem. So now you work on the theoretical part of that mathematical concept that is needed to solve that problem. You create the entire machinery. You really understand what's going on. You gain a deep knowledge of the tools of mathematics that you are creating, all with the motivation of solving that problem. That's the second step. The third step is to use the tools that you have just created in the second step. Use the tools of mathematics to solve that motivation problem. So these are the three steps. And in this particular video, I will use it to solve a problem which is often used in data science. I will use a very simplified version of it. So the motivation problem is this, that we want to find out similarity between images. So imagine you have a folder containing millions of images, and it's known that some of them are dog images and some of them are cloud images. Now, without going into one by one, you want to distinguish between the two types of images, the dog images and the cloud images. This is related to a very much bigger problem that is often used in Google search and other image search algorithms and stuff like that. But I'm just using a very simplified version of that problem. So here are three pictures. Of course, we will start with small number of things to understand what's going on. But the same principles can be applied to millions of pictures. So look at these three pictures. The first one, the image 1, is of a cloud. Image 2 is of a cloud. And image 3 is of a dog. So what you want is to create enough mathematics which can distinguish between these images. Okay. So how do you do it? So what you do is you use a mathematical concept called directional cosines and angle between vectors. In fact, more precisely, we will be using something called dot product. Maybe you have seen it before, maybe you have not. It will be fun to see how we can use dot product to do this image classification, or rather distinguish between the images between clouds and dogs. Okay, so this is part of analytical geometry. The final picture would be something like this in the three-dimensional space. But in this particular video, we will work in a space whose dimension will be 90,000. It's quite exciting, right? So let's start with the basics. What mathematics we need to really solve this problem? So first, let me draw some pictures. So you have an image here, and all the images that I will be using, for the sake of simplicity, they are 300 pixels cross 300 pixels, 300 by 300. So what does that mean? That means that you can divide the image into 300 columns like this, and 300 rows like this. And each box, which is basically a pixel, has value between 0 to 255. So all of the images that I will be using are grayscale. They are not colored images. So 0 here means pitch black, and 255 means white, And all the numbers between 0 and 255 will be some sort of gray. Okay. So what I want is, I want to start with that image file and create this grid. So this grid will contain numbers like, let's say, 31, 252, 32, something like this. So all of these boxes will have these numbers, and these numbers will represent how gray that particular box is. And all those 300 cross 300, so there are 90,000 boxes in this small image. All of them will together create the image. So we want these numbers to represent how gray a particular area of the image is. Okay, so that's the first thing we want to do. So let me write that. So we have this image 1, let's say, and we want to convert this image into a grid of numbers like this, and each box will contain a number between 0 and 255, representing how gray that particular box is. And in fact, from this grid, I would like to create a vector. Vector means it's basically a list of numbers. So let's call it list 1, a list of numbers. So what I'm going to do is, I'll just take the first row of this grid, and place the 300 numbers here, one after another. And then I will start with the second row and just place it beside it. So like this. So this is the second row. This is the first row. First row of this grid, second row of this grid, and so on. Okay. So how many entries will be there in this list? Well, there will be 300 times 300. So 90,000 numbers will be there in this. 90,000 numbers will be in this list. So you can think of this as a point in the space of dimension 90,000. Like a list of 3 numbers. Let's say if I put it like this, let's say 2, 5, -7. A list of 3 numbers can be imagined as a point in the 3-dimensional space. It's a coordinate point. Similarly, these 90,000 numbers can be regarded as a point in the space of dimension 90,000. Of course, we have no way in imagining it. It's mind-boggling. We can just write it down. So what we have done in this process, we started with an image, we produced a grid, and from that grid we produced a list. So we would like to do this thing for all the 3 images. So let me just put it here. So this is image 1, and this is, let's recolor this into red. This one will be image 2. This is image 2, grid 2, list 2, the second image. And similarly, we would like to do the third one. Let's put that one in blue. Okay. So this is image 3, grid 3, list 3. Okay. So we have 3 different images, and what we have done is we have produced 3 different lists, which we are now thinking as points in a space of dimension 90,000. So what do we want to do? We want to know which images are similar and which images are different. So similar images will be either images of dogs or images of clouds. Dissimilar images will be dogs and clouds, like this, different. Okay. So let me show you how to implement this thing in a code. In fact, this is a very nice practice. When you are talking about the motivation problem, you can actually show or do an implementation of that practical problem. If it's a problem in computer science or data science, it's easy to do. So let's go ahead and check this out. Fired up the Anaconda, which is basically a platform to write codes and do all sorts of data science stuff. So here is the situation. We have 3 images. I showed you in the previous section the 3 images. There is an image of a cloud, another type of cloud, and then there is a dog image. So what we want to do is to distinguish between these 3 images. And I told you in the previous section theoretically how we can do it. Now let me show you practically. So basically I have created 3 images, sort of opened 3 images, image 1, image 2, and image 3. I have opened the first image, second image, which is named cloud2g.png, the third one, which is dog.png. And then I want to convert this. Remember what I wanted to do? Take the image, convert it into a grid of numbers, a matrix of numbers, 300 cross 300 matrix. So this is my data 1, or if you want, I can just do it grid 1, whatever, I can give whatever name. So this is basically a function from the NumPy package. So I'm doing this in Python. So basically I am extracting the information of the image and producing the grid of numbers. So I can show you how it looks like. Let's say if I want to print data 1, the first one, which is basically extracting the image 1 as a grid, converting the image 1 into a grid. So if I do that, it basically produces a grid. If you can see it, this is a grid of numbers. It's not showing the entire grid, showing like part of the grid. But notice that all the numbers are between 0 and 255, as we mentioned earlier. 0 means pitch black, 255 means white. So this is the data 1, the first one. If I do the same thing with data 2, okay, let's do it with data 2, the second one. So you see that grid changed, right? Because that's a different image, so the grid changed. And the third one, let's do data 3. And let's do it. So again, the grid changed. So 3 different images, 3 different grid or matrix of numbers. Each of them is 300 cross 300. Okay. So we have this. Now what we want to do is we want to convert this into a list. It's a vector. Remember I told you there are 9. All the 300 times 390,000 numbers will be in a single sort of a vector or a list of numbers. So that's what I do. I create the list 1, which basically unravels data 1 and converts it into a list. These are very simple and well-known methods in functions in Python. So I do this for data 2, that is the second image grid, and data 3, which is the third image grid. So for fun, let's look at how many elements are there in list 1. Okay, so in list 1, so let's print it. Print the number of elements in list 1. So this is just len is the length function. This len is the length function, and it tells us the number of elements in list 1, and then we print it. Okay, so let's try that. So if I see 90,000, exactly what we wanted, right? 300 cross 300 pixels. So 300 times 390,000 numbers. And in fact, I can print the entire list 1, which will be a pretty large list, like 90,000 numbers. But let me do it for fun, just for once, because I mean, when you see it, you believe it. So let's do it. Okay. So here we go. The 90,000 numbers. I can just scroll down and down and down and down and down, and it seems unending, right? So this is the thing. So we have done this for, so okay, I'll just go back to it. It's pointless to just scroll down all of these numbers. So, okay. So now we have this 3 images converted into a grid. That grid is converted into a list, which we are thinking as a point in a space of dimension 90,000. All of this we want to do to distinguish between the cloud images and the dog image. So the next part, let's develop the mathematical tools necessary to do this check. we will use mathematics. In fact, we will use dot products and the angle between vectors, this idea of angle between vectors, to solve this problem. And you will see how beautifully you can distinguish between clouds and dogs, and how beautifully you can see the similarity between clouds and clouds. Okay, so let's go to the board and do the mathematics. Okay, so I'll tell you the fundamental geometric idea that we will be using. And since we cannot draw a 90,000 dimension space, we will be drawing a 3-dimensional space. So let me draw the picture. It will say everything that is there to say. So we have the 3-dimensional space. So let me draw the axis. This is the x-axis, this is the y-axis, this is the z-axis, okay? And all the positive directions, like this. And we want to think of each image as a point in the space, okay? So we have a list of numbers. We are thinking that that list is the coordinate of that image, the coordinate. So if I draw, let's say in 3-dimensional case, if it is 1, 2, 3, this is the list, then it simply is a vector like this, a point in the 3-dimensional world. Of course, the images that we created is a 90,000 dimension thing, because the list contains 90,000 numbers. This list contains 3 numbers, so we are drawing it in the 3-dimensional space. Okay, so let's call this V, this particular point. V represents an image. An image, actually the data that represents an image. Okay, so let's call it V, and then we can have probably another one. Let's say W. So this is 3, 7, 9. Let's say another point. So I can draw that here like this. So it's not drawn to scale. I'm just drawing random points. Okay. So V and W are here. What we are going to say is that if the angle between these two vectors is small, if the angle between these two vectors is small, then they are similar. If the angle is large, they are dissimilar. Okay, so let's call this point O. So I'll write it to explain one more time that each image is a point or a vector. Two images are similar if the angle between them is small, and if the angle between them is large, then they are dissimilar. Okay, so this is the angle that we are talking about. This is the angle theta. So how do you compute the angle theta? And there is a very famous formula, which is cosine of theta, cosine of the angle theta is equal to the norm of the two vectors, the length of the two vectors, actually the opposite, the dot product of the two vectors divided by the norm of the vectors, product of the norm of the vectors. So this is a formula that we really want to understand. You know, it is the case that many people know this formula, but they don't know how to think about it. Where does it come from? Okay, so in this particular video, we will actually go into that depth. We will try to understand it. Okay, once we understand it, we can now apply the same concept in the 90,000th dimension and find the cosine theta between the image 1 and image 2, image 1 and image 3, image 2 and image 3, like that. Okay, so where does this formula come from and what does it even mean? So if V, let me write it like this, if V is equal to, let's say, V1, V2, V3, these are the three coordinates, and W is equal to W1, W2, W3, then V dot W is simply, you just coordinate wise multiply and add. Coordinate wise multiply and add. Okay, so that's how you get the dot product V dot W, and you want to divide it by the norm, the length of the vector from the distance of the point from the origin, which is simply using Pythagoras theorem. This is square root of V1 square plus V2 square plus V3 square times square root of W1 square plus W2 square plus W3 square. That is the ratio that we are after. Okay, so all right, that's fine. But why is it the cosine of theta between the two vectors? Why is it so? Okay, so I'll remind you what cosine of theta is. If you have a triangle, let's say ABC, and it's a right angle triangle. If it's a right angle triangle, let's draw a right angle triangle. Then, if this angle is theta, cosine of theta is equal to BC over AC, the hypotenuse. So it's adjacent over hypotenuse, right? So that's what cosine of theta is. But there is another way to think about cosine of theta. So if you want to work with any triangle, ABC, and suppose this angle is theta, then there is a formula called the extended Pythagorean formula, which is like this, that AB square plus BC square minus 2 times AB into BC times cosine of theta is equal to AC square. So AB square plus BC square, the two sides that are containing the angle theta, AB square plus BC square minus twice AB BC cosine of theta. Okay, so if it was a right angle, then this part, that if theta is a right angle, then this part becomes 0. This part becomes 0 and we get the Pythagoras theorem. But if it's not a right angle, then you have this formula. Now, we can go ahead and try to derive this formula using the Pythagoras theorem, but we are not going to do it in this particular video. I have done it numerous times in other videos. In an actual class, I would actually go ahead and prove this particular formula. It's quite simple. What you have to do is you just drop a perpendicular from here. Let's call it D. You drop a perpendicular like this, and then you try to do the measurement of AC square with the information that you already know. Okay, so it's not hard at all, but we will not be doing it in this particular video. So this is the formula that we have to keep in mind. This is the cosine formula. Okay, so what is cosine of theta then? Cosine of theta, so you can just isolate cosine of theta, is simply AB square plus BC square minus AC square divided by twice AB into AC. Okay, so this is what the cosine of theta is. You just rearranged it. Now, what is happening with the vectors? So when you are working in the world of vectors, what happens? So if you have a vector, so I'll just draw it schematically. You have a vector which is v, and you have a vector which is w. Then the resultant, or the third side, if you draw it like this, is w minus v. W minus v, right? So this is very simple. This is from congruency of triangles and parallelograms, stuff like that. You can prove this rule of vector addition quite easily. And you should, if you don't know how to prove this, you should prove this using elementary geometry. It's not hard at all. But again, we will assume that this is known. So now, if this angle is theta, then we can use the cosine formula that we just have from above. And the cosine formula is this, that the cosine of theta is equal to the norm of w square. So the length of w square plus the length of v square minus w minus v square, right? So these are the two things, and divided by 2 times norm of w, norm of v. Okay? So now you will see something really interesting happening. Norm means just the length, okay? So you can just calculate this. You can calculate this, and we will do this calculation actually. So what is this? The first one, so cosine of theta is equal to, the first one is w1 square plus w2 square plus w3 square. This is norm of w, or the length of w whole square. And then we have the length of v, so this is v1 square plus v2 square plus v3 square. And then we have this, so this is w1 minus v1, w2 minus v2, w3 minus v3 square. So you can just check w minus v. So what is w minus v? What is the coordinate of it? It is simply w1 minus v1. So coordinate wise subtraction, right? So w2 minus v2, that's the second coordinate. w3 minus v3, that's the third coordinate. And then if we take the norm of it, or the length of it, then you just have to take the square of each of the coordinates and then take the square root of that. And here we want the square of the length, so we have this, okay? Anyway, so the denominator is simple enough, 2 times wv. And if you do the expansion, you will see that in the numerator, the only thing that's remaining is 2 times w1 v1, w2 v2, w3 v3 added up, divided by 2 times wv. So we just discovered the dot product in a certain sense, because 2 cancels off, and this numerator is v dot w, exactly what we wanted. And the denominator is v, length of v times length of w. So we exactly know now why this formula works, provided you believe the cosine formula that I just gave here, this one. And that you can prove using the Pythagorean theorem, which you can prove via a variety of methods. One of the oldest methods is by Sulva Sutra. I have discussed it numerous times in other videos. You can check our YouTube channel or other places as well. So it's all coming down from geometry. And this gives us actually confidence into what's happening. We understand why the dot product is useful to determine cosine of the theta between the two angles, the two vectors, right? So now what we have is we can just calculate cosine theta between v and w, or the two images, by this particular formula, right? So let's do that. Let's find out the cosine of the angles between the three images, pairwise three images, and see which one is nearer to which one and which one is farther away from which one. It will give us an idea about how much similar they are, how much dissimilar they are. So we'll get back to the code and do the computation now, because there are 90,000 numbers and we cannot hand compute it. So we'll use a computer. Remember, we are back in the motivation problem. We started with the motivation problem. We deduced the mathematical tools and intuition from scratch. And then we now want to use those tools to solve the motivation problem. That's the third step. So here, I'll remind you, we started off with three images of cloud, and dog. We converted those image information into grid information using this asArray function, which is part of the NumPy package. And then we converted those 300 cross 300 matrices into lists, each of them containing 90,000 numbers. Now we are imagining them as points in the space of 90,000th dimension. We want to calculate the angle between those images, and those angles, the cosine of the angles, will tell us how similar they are or how dissimilar they are. Okay? If they're very similar, they are either both cloud or both dog. If the two images are dissimilar, then they are of different kinds. That's the guess. Okay? So I have really done three things. I'll just show you the third part. It's very simple. It's just math, but it's just the cosine theta formula, that is v dot w divided by norm of v times norm of w thing, written as in a code form. But I've done it in a way so that you can understand, you can read it out. For example, the first part says this is sim1. Sim1 will give us the cosine of the angle between image 1 and image 2. Sim1 is simply the numerator. So there are two parts. There's a division sign. There are two parts. The numerator is basically the sum of r times t, r from list 1 and t from list 2. So what this code will do, it will take in the first entry of list 1 and the first entry of list 2 and add them up and multiply them. And then it will add to that, again, r becomes the second entry of list 1, t becomes the second entry of list 2, and they are getting multiplied, and they're getting all added up. So this part is basically the code for the dot product. You are picking up r and t from list 1 and list 2, you're multiplying them, and then we are adding up. Okay? The same thing, it happens in the denominator. This is math square root function I'm using. Okay, so this is from the math package. So it's pretty simple. We just take s from list 1. So list 1 has 90,000 numbers. We take each number, we square it, and then we add it up, and then we take the square root of that and multiply to that the second list. Okay, it's pretty self-explanatory. So we do this for list 1 and list 2, that is the first two images. List 2 and list 3, that is the second two images. List 1 and list 3, which is the first image and the third image, right? Okay, so now let's go ahead and execute it. Let's see what we get. So let's see what we want, what we expect to get. We expect image 1, which is cloud, and image 2, which is also cloud, to be very similar. So their angle is very small. So their cosine is almost 1, because cosine of 0 is 1. So something which is very small, the angle is very small, cosine of that angle will be close to 1, like 0.9 something. But if you compare image 1 with image 3, they are cloud and dog, their cosine should be much smaller than 1. Similarly, image 2 and image 3, their cosine should also be much smaller than 1. Okay, so image 1 and image 2 should give us a large cosine closer to 1. Image 1, image 3, and image 2, image 3 should give us smaller cosine values. Okay, so let's do that. Okay, the similarity cosines, we got it. Image 1 and image 2 is 0.92, which is pretty close to 1. And that's expected. Cloud 1 and cloud 2, both of them are cloud images. Look at what happened for image 2 and image 3. It is 0.77, right? It's much smaller. And image 1 and image 3 is also much smaller, the cosine of the angle between them. So, of course, this is a very, very simplistic view of what's going on. There could be a ton of other things that goes on, and the actual image classification problem is much harder. But really, the goal of this particular exercise was not to teach you image classification, was to teach you the math. But we used a motivation problem to, spice up the matter and put our learning into work. That always is a good thing if you put your learning to work. Okay. So I hope you enjoyed this session. If you have some similar ideas, let us know in the comment section. It would be really great to get some user feedback, the viewer feedback. If you like this kind of stuff, please subscribe and join our channel. And if you want courses in mathematics, statistics, computer science, physics, Olympiads, some outstanding programs are there. Check the link in the description. Thank you and stay well. I'll see you in the next video.